Hey, I just wanted to walk through an example that I had skipped over in class, but give an example of kind of the total derivative and breaking it into the variation of a function into its various parts and into the various ways in which it might vary. So my example is going to be looking at the Stefan Boltzman law, and this describes the power radiated by some object given its temperature and size. So there's a constant here, the Stefan Boltzmann constant, which is measured in watts per meter squared per Kelvin to the fourth power, because the power here is proportional to the area of the surface area of the object, as well as the temperature, in this case, to the fourth power. So it's highly dependent on temperature. So what I want to do is say, okay, let's think about the sun and how much total energy is radiated from the sun. And we could calculate the power, the total luminosity of the sun using this equation. We know the sun's temperature and its size, so we can calculate this. But what I'm actually interested in is the sun's not going to stay at the same temperature and the same size forever. In fact, our sun is going to eventually become a red giant star, and so it's going to get a lot bigger, and then actually as it does so, the temperature is actually going to decrease. So the temperature will go down, but the area will go up, and so we don't know exactly how this power is likely to change as it does so. So to figure that out, we can use this total derivative. And so here, what we want to do is we say dt, how is the power going to change as a function of time, will be d dt sigma a t to the fourth power. And here, we're going to take our total derivative of this. We're going to have a component that varies as the area varies and a component that varies as the temperature varies. So we'll have sigma t to the fourth times dA dt. Or rather, let me take one step back. We could say first, this is the partial derivative of p with respect to a times dA dt plus the partial derivative of p with respect to t dt d little t with respect to time. And then we can evaluate those individual partial derivatives to get sigma t to the fourth dA dt plus dp temperature would give us 4 sigma a t cubed dt d time. Okay, so we have now these expressions. We could also try to figure out, well, the area. We're talking about the surface area of the sphere, so we might also want to think about sigma t to the fourth. Now we have d dt of 4 pi r squared here, because that's the surface area of our sphere. And of course, let's have this term. That. Finishing off this derivative, we have sigma t to the fourth. This is going to give us a 4 pi coming out, but then we would get a 2 down from the radius, because the radius is changing with time as the star gets bigger. So I'm going to actually make this an 8 pi r dr dt. So now we've accounted for the variation as the radius changes. How does the radius change the area, and how does the area change the power? And then we still have this term 4 sigma a t cubed d temperature d time, like that. Sorry, stepping off the screen. Okay, so then we have effectively everything we need to finally plug in some numbers. We know the size of the sun, the radius of the sun is about 700,000 kilometers, and the temperature is about 6,000 Kelvin, and we know the value of this constant, so we can just start plugging in numbers, assuming we knew something about what the dr, dt, and d temperature, d time derivatives are going to look like. And if we make some assumptions about that, we could say plug in some numbers. And in this case, we would end up getting something on the order of, given estimates of models for how these things vary that we're not going to get into because that's a whole lot of astrophysics, but we would end up getting something on the order of 1.3 times 10 to the 13 watts per second. And we check the units here. Watts is a unit of power per time, so watts per second. The units check out. We can also walk through our units in this equation here through all of our different terms. We know this is a rate of energy with respect to time, power divided by time, watts per second. And then if we followed carefully all the way through here, which you can try to do, or you can follow the posted notes where I do this, see how the units of all this should, of course, add up to watts per second, or energy per time squared, for this all to work out and make sure the units of the equation work. So this is another example of doing this total derivative, seeing how the function varies in a couple different parameters that are all varying with respect to time, and then making a calculation based off of that. So that was an example I skipped over. So hopefully that's useful.